I want to thank Rachel and Jeff, actually, for inviting me to this, because this is an amazing event, especially for something that's only been going in Austin for a year. So this is fabulous. Yay, Astronomy on Tap, guys. So the topic of my talk is why you should give a rat's ass about pure science research. And tragically, they would not let me title the book that. I thought it would sell a lot better, right? Would you not buy a book that said why you should give her? Yeah, you would totally do that. And they said, no, it's a little too edgy. So, but why I came up with something like this, well, something that might be a little familiar to you. Right, you hear these sorts of things, especially if you're trying to get a grant, or you're just interested in science, and then you hear things like the federal government has awarded too many grants that few Americans would consider to be in the national interest, and you wonder, what is this person thinking? Okay, and so I just basically I beat my head against some hard objects for a while, and then I went, don't people understand, that weird things like pondering the nature of space-time, don't they understand that actually turns into something really amazing sometimes? And even if it doesn't, is it not just amazing, right, that our brains can wrap themselves around any of this, right? And so it was actually things like this that turned into this. Tragically, not why you should give a rat's ass about pure science research, but it turned into this, and I was happy about that. And I've got a box of them on sale. Just wanted to mention that. But the thing is, this is the sort of thing that comes, and I actually started hearing this when I was an undergraduate, and I took some astronomy courses at the same time that supernova 1987A went off, and I was like, wow, that's so freaking cool. And the guy that was teaching my intro astronomy course happened to be a neutrino guy, and he said, wow, they've discovered all these neutrinos that came from the supernova event, and I'm so excited about this, and I'm trying to tell somebody, and that person said, why should we give a rat's ass about this? What difference does it make? Who cares? When's this ever going to matter to me? Actually, I think their exact words were that and 50 cents will get you a cup of coffee, but then that was 1987 cents back then. And these are actually the sorts of questions that scientists have been hearing as long as there have been scientists, is why should we care about this kind of thing? And so here's actually probably the best response ever to this. It was J.J. Thomson. This is a guy who discovered the electron, right? So he's a pretty heavy hitter. And he got so sick of hearing any of these questions that he had a toast. He actually would toast. To the electron, may it never be of any use to anybody. Right? Which tells you a couple of things. One, he was pretty secure in his position, but two, scientists have no clue where their discoveries are going to go, right? I mean, we're talking about the electron. May it never be of any use to anybody? Whatever. That's a nice try there, but and there are some other fairly heavy hitters that have been fielding this question for a couple of centuries. Back in 1816, Michael Faraday, who, again, he's a guy that shows up in your textbooks, would give talks. And he was so accustomed to hearing the what good is it question that he would say, I will point out his history as an answer to those who are in the habit of saying to every new fact, what is its use? Dr. Franklin, and that's Ben, says to such, what is the use of an infant? Someday it will grow up. Right? And so, but here on the 100th anniversary of relativity, you gotta wonder, how is relativity going to grow up? These are some strange ponderings that Einstein was having about the nature of space-time. And, let's face it, we're still learning Newton's gravity because it works, right, for just about everything that you will ever deal with. And so it seems kind of odd that we should even care about the stuff that this guy was thinking about 100 years ago, 110 years ago. Okay, and one of the things that as we found out in the last talk, that relativity tells you is that matter affects time. Okay, now we get to the question of what the heck is time? And what the heck is space, really? I mean, when you're saying this is going to warp space-time, what are you talking about? And this is one of those things that people have pondered pretty much for as long as there have been people. The concept of time through time, if you go back to Aristotle, he had sort of an interesting sort of circular definition that without motion there is no time, and without time there is no motion, and it kind of just spiraled in on itself. You go up to about 400-ish AD, and you've got St. Augustine, who said in his Confessions, kind of an odd book to have a treatise about space and time, but whatever. But within there, it actually basically said that time is sort of is part of the package deal of the universe. And this was the answer to a question about, what was God doing before he created the universe? He had apparently a lot of time on his hand, and the uncharitable response that the bishop was giving at the time was creating hell for people like you who ask these questions. And Augustine figured that may not be like the most inviting way to put this, but he thought about it. Time was something that came with the space, it came with the stuff, okay, and that was a supremely Einsteinian kind of thought. And then you've got the guy who we seem to revere, Newton, right? Think about any physicsy class you've ever had. You've got space is your X and Y and Z, right? And then you've got time. It's an entirely separate thing, right? And even your X's and Y's and Z's, you split those out into their components and solve problems that way. But time was not part of that. And as far as Newton was concerned, time is just one of those universal absolutes, and it just is, right? So here's your score right now. Your theologian is winning. Aristotle, we get partial credit for that. The physicist, we actually get 0 for that one. But, Newton had a bunch of other things on his mind. But it does turn out that time and space and matter seem to be woven together, right? The one that came up with sort of the codified version of this is Einstein, right? And that's why we celebrate this 100th anniversary of relativity, okay? And that's all special and everything. But again, who gives a rat's ass? It's great mental gymnastics, but what difference does it make? And it turns out, well, if matter is going to warp space, which it does, right? We saw the little demonstration where you put the heavy ball in and it warps, and it's kind of odd because you're using the phenomenon to show the phenomenon in this one, right? The fact that you've got gravity pulling down on the ball that's in there so that you can do a demonstration about gravity warping the space. Whatever. I just get in the endless loop on that one. But if mass is warping space in an observable way, okay, mind you, it's not just some kind of weird ponderings, it's in an observable way, then it also has to warp time. And I will do a plug for Interstellar, because I just thought that was a really cool movie, especially visually anyway. And again, as you get closer to a massive object, time ticks more slowly. It's like it's stretched out. Now you get into a black hole and it's stretched out so that your time grid lines are infinitely far apart and time seems to stop, which is weird because we don't know why time started in the first place. Right, so you think about a black hole, is where this stops, but why is it there at all? But the thing is, little kids are potently aware of the fact that time ticks more slowly the closer you are to a gravitating object, right? Because when you're short, Christmas is forever away, right? And I'm up here on the stage, and so it's actually ticking a little faster for me than it is for you. And you get up to the, the third floor of a building, and it's just, wow, it just goes crazy. All right.
I want an Xbox.
Talk to Santa. All right. Now, one of the experiments that was done to measure the warping of space by a gravitating object was done in 1919 by Sir Arthur Eddington, who went to see how the stars' positions, okay, in a particular cluster, in the Hyades cluster, changed when the sun was in the way. Okay, except the problem with the sun being in the way is that it kind of outshines the stars that are in the cluster, right? And so you have to wait for an eclipse, and a perfect opportunity for this happened in 1919. And so here's Eddington, and there was actually another expedition that went to measure this effect of the stars not appearing to be in the right place because their path was curved by the sun's presence. Okay, it was warping the space that was in between us and the Hyades, and so the stars looked like they were out of place. And this was amazing. We got the New York Times had this wonderful headline, not remotely hyperbolic there. Lights all askew in the heavens. Oh my gosh. Einstein became a celebrity, and there was this amazing little newsreel that was done. Okay? But let's get real. This kind of measurement can be done with relatively mediocre telescopic equipment. Okay, they did not schlep Hubble Space Telescope somewhere, right? They just took some telescopes that they could set up by hand to measure this warpage of space. Okay, trying to measure how it warps time is a whole different ballgame. Okay, your mediocre clocks are not going to cut this. To give you an idea of how little the time is stretched out when you're down at sea level, your year is about 30 millionths of a second longer than the year atop Mount Everest. Okay, that's not that much. You need to have a pretty amazingly fine-tuned clock to measure a difference like that. Okay, but thankfully, this is one of those things that scientists got their brains wrapped around. At one point in the 1800s, somebody realized that any mechanical clock that we would ever create is going to wear out. It doesn't matter what kind of thing you create, it is going to eventually wear out if it's got, some kind of pieces to it. But one thing that doesn't wear out, that always, as far as we know, behaves the same as the atom. And so it was actually in 1879 that Kelvin had the idea, it would be really, really cool if we could use natural transitions in an atom to measure time. But it took another 70 years before we actually figured out how the heck to do that. It was not so easy. But in 1944, they were planning a cosmic pendulum for a clock. And that's kind of an odd thing considering, I think of cosmic, I think really big and great. And this is really a small pendulum that they were thinking was a useful thing to use. And that was an ammonia molecule. Now here's the clock. This is the first atomic clock. This is in 1949. This was kind of the photo for their press release, I guess. And the thing is that the photographer's going, it doesn't look like anything. Can we put a clock on top of it to show what this is? At this point, 1949, we don't have really a lot of plans to do anything in space, but somebody did get the idea, it'd be really cool is if we could take one of these things and launch it out into space somehow, and then we could measure that time difference, because this was getting closer and closer to being up to the task. Okay? And, this is the type of thing that even made Ripley's, believe it or not. I love it, though. It's the most accurate time machine in the universe. It is even more accurate than the movement of the Earth. Now, let me tell you how accurate the movement of the Earth is. We have a severe earthquake that changes the rotation rate of our planet by milliseconds. Right? That's not very accurate. So, But whatever. Alrighty. So fast forward about 20 years, 22 years actually, from the first atomic clock. We're 15 years after Einstein's death. Okay, so he never got to see this, but it didn't matter because he knew the way it was going to come out anyway. And we finally have basically portable atomic clocks. For a while they grew much bigger, but then we figured out how to make them smaller and relatively portable. And so a couple of guys at the U.S. Naval Observatory got the bright idea, hey, let's take these atomic clocks and get them up off the planet, okay? Get them elevated. Couldn't exactly just throw them on a rocket, so what we did was we put them on 4 commercial jets. They're just regular old everyday jets that made stops at various places to let people off and get new people on. And so they took 2 of these jets around the planet in one direction, and 2 of them all the way around the world in the other direction. Now, you've got the rotation of Earth, all right? So your relative speed has to be sort of calibrated. You're not really going the speed of the jet. You don't roll that into your special relativity. You got to figure out, are you going this away with the planet or that away with the planet? But they went ahead and they bought some tickets for Mr. Clock and Mr. Clock and Mr. Clock and Mr. Clock, right? And what they wanted to do was to measure the time that these Mr. Clocks gave as a result of both the speed of the plane and the altitude, as it did all of these various stops on the way around the world, and compare the final answer to a clock that they had calibrated against that was already that was just staying there on the ground. And so they did that. They wrote a paper. There's the 2 guys on the plane with Mr. Clock. Okay, and they measured time differences in the nanoseconds. And their conclusion: these results provide an unambiguous empirical resolution of the famous clock paradox with macroscopic clocks. And that was something that you could do something with, right? Now you know if you get off this planet, your time ticks along at a different speed. Now you know if you go this way versus that way relative to the rotation of the Earth, your time ticks along at a different speed. And so when you finally get to the point that you're launching some satellites out there that are supposed to keep an eye on where you are, and you're really keen on knowing exactly where you are, then you have to worry about how fast are these things moving and what's their elevation. Okay, and they're not all moving the exact same direction, so you got to get all that factored in there. And these guys all have atomic clocks, and they've got relativity incorporated into them, okay? And if they didn't, you probably wouldn't find the place that you want to find. Okay? In very short order, the signals are going to get your position very, very wrong. And this is not just because you want to be able to find a restaurant without a map. If you're flying an airplane, it's kind of handy, right, to know precisely where you are and to have the GPS actually working. And so what that really boils down to is that we get back to what Faraday said. People probably gave Einstein, they tried to give him too much grief, but somebody somewhere probably said, what good is all this stuff? What difference does it make? Why don't we just keep on with Newton's? It mostly explains everything, and that Mercury thing, whatever. Its orbit isn't exactly right, but we're cool with that. Okay? But it has grown up over the past century into something that allows me to say, I found this place. I drove all the way from Huntsville, Texas, and I got here. It was really neat, It took me half the journey just to get down 35. But the question that you should ask yourself, and maybe you should ask your representatives, what is it that's being done today that people would say, what's the point? Too few Americans think that this is worth funding. What is it that's being done today that in a century is going to be a life changer? Think about how long it took for relativity to actually mean anything in anybody's life. Okay? And really more important, who exactly is qualified to make the judgment of whether or not this is important research? Is it that guy? Is it politicians who have had a science class? Okay, or maybe it's the scientists. Maybe, right? They seem to, that's kind of competitive. You're not going to give somebody a grant unless you think that they're going to do something useful with it. It might be a game changer, it might not. Who knows? I mean, heck, most startup companies never go anywhere. Right? But for some reason, all scientific pursuits are supposed to go somewhere, like within the next election cycle. Right? So we can hang that one. And so, here, my public service announcement for the day really is that obviously I'm preaching to the choir, but most people don't really realize that GPS has anything to do with anything weird like relativity. People don't seem to understand that their Wi-Fi has a component to it that would not be here were it not for the fact that there was some guy in the 70s trying to find exploding black holes. Yeah. Or that you couldn't do really rapid DNA typing if it weren't for some guy that happened to notice some yellow slime growing in Yellowstone and then tried to culture it and failed. So there's tons of examples of things where people just went, ooh, that's weird. I want to know what that is. I want to see if I can try to find that. A lot of times they failed, but then they wound up changing your life. And that's in that book, right over there, right there. And that is my time. Oh, wait. I do want to mention that I love the internet because you can find things like a picture of a rat with its ass.
All right. Thank you very much, CosmiCat. And we have time for some questions. We're going to start with one from Twitter. With all the GPS and other technology, explain how things like Air Malaysia seem to completely disappear from the planet.
How things like what?
The Malaysian aeroplane. It's all right. You don't have to have an answer.
Maybe they wanted to know what it was like to fall into a black hole. I don't know. It's still a very big unexplored planet, really. I mean, let's get real. There is still so much of the planet that we live on that we don't know about, right? And the ocean's a big, big place, and I don't think people really appreciate the bigness of it until they take a trans-Pacific flight, and then you realize just how big that is.
All right. Any questions?
To Einstein.
Oh.
May he never be of any use to anybody. Oh, wait.
Okay, there's a question just down here.
Do I see emerging technologies that are exciting? It's a kind of a personal question, really. I gotta say, I'm very much, just in the cerebral, isn't this a neat fact kind of person, and so I trust that other people are trying to emerge technologies, and I'm cool with keeping up with them. There is one thing that I talked about in my book, and that is how trying to understand the composition of the sun is potentially turning into a cancer treatment. Okay, but that's one of those things that's kind of on shaky ground right now, and is because the technology that's required to do what they want to do isn't quite here, and so it might fail, it might do something.
That's pretty cool. Okay, we've got a question right down in front here.
Oh, now you'll talk to me. Never mind. Not anymore.
How many scientific experiments do you think will fail and turn into something that will go, hey, this is really, really cool?
Okay, so the question was, how many scientific experiments do I think will fail for every one where we go, wow, this is really, really cool? And even the failures are cool, right? The guy that was trying to find exploding black holes, didn't find them, totally failed. They found all kinds of other things. We still haven't found exploding black holes. but eventually it became the underpinning of Wi-Fi. And, it's like anything else. If you look at the numbers of musical pieces that Beethoven wrote compared to the ones that anybody actually listens to, right? It's just in the hundreds, thousands of things that he did that would be considered failures. But that's part of creativity. Right? You're going to have a heck of a lot of failures before you have a success in pretty much anything. So, I mean, I can't give you a number on that one, but it's a whole lot to one.
That's a good answer. Any more questions? There's only at the top, I can't really see.
Yeah.
Down here in front.
All right, I'll ask you to speculate on something. Let's say we go back to 1900, before Einstein's discoveries, and say it's taken Rutherford only 20 years to get an atomic clock. And let's say also we had the ability to put up a bunch of satellites and came up with the idea of GPS. They launched a constellation of GPS satellites, and they take their measurements and they found out that they're 10 miles off. Think of all the physicists who were working in 1900, how would they react to that?
I don't know. I can't even begin to speculate on that one. I mean, I know when they originally saw that Mercury wasn't orbiting the way that it was supposed to, that they came up with a dozen explanations. Extra planets, right? We had Vulcan for a while, which would have been really wicked. But no, we don't have it. But I mean, we probably would have tried to come up with reasons why it wasn't working. I'm not sure we could ever have an empirical correction for relativity, right? That you just realize it's off by a certain amount, so you just build that into it. I think that would be just way too much of a reach without an Einstein there.
Okay, we need to wrap up, so let's say thank you very much to Dr. Renee James.